All right, here we go into our intro to Taylor polynomials. In this activity, what we're trying to do is kind of get an introduction to one of the biggest concepts in this entire Calculus BC course, which is Taylor polynomials. And so we're going to start with just the concept of we want to create a function that will approximate the cosine function, okay? So we're going to do a step-by-step process to kind of get into how a Taylor polynomial comes to be. So step one in our process is we're going to find the equation of the line of the tangent line of cosine at x equals 0. So if we go to our cosine function, when x is 0, we are right here. The tangent line, I don't have to do anything fancy because I know the tangent line here would be horizontal. So to write the equation of the tangent line, I could simply say the equation would be y equals 1 because it's a horizontal line through 1. Sketch your linear approximation on the graph at the right. Okay, we got that. Notice that our approximation has the same y value and slope as the original function. What other property could be used so that it matches at the point x equals 0? So basically, I'm saying that cosine of 0 is 1, and my tangent line at 0 is also 1, so they have a point in common. They also have a slope in common. So the slope of this line is 0. The slope on cosine at the original location is also 0. So we're saying basically the original functions are the same for cosine and the tangent line. And we're also saying that the derivatives are the same because we're talking about slope. So what other property could be used so that it matches at the point x equals 0? We could also use maybe concavity to describe to get a better idea, which we're not seeing that here so much because our tangent line is horizontal, but that won't always be the case. What degree polynomial would this approximation need to be? So if I wanted the concavity to match the concavity of the cosine function right in this region, I would need to have a second degree polynomial. Because if you were just to zoom in on the cosine function right here, it looks like a quadratic. Okay, quadratics are second degree. All right, so let's do that. So we're going to do an approximation technique here. So we're going to start with the function we are approximating is y equals cos of x. And the quadratic approximation, that's going to be just the standard form of a quadratic equation, which again, we don't know what a, b, or c would need to be to make a quadratic function that kind of hugs this curve here. So we're just going to start with something very basic and just call it ax plus, or a plus bx plus cx squared. You could even flip this around if you wanted to. Anyway, if we take the derivative, so that's going to be our next move. If we take the derivative of this, we would get b plus 2cx. If we take the derivative of cosine, we would get negative sine. Then it says take the second derivative, so that would give us, what, 2c? And the second derivative over here would give us negative cosine. Okay, so all this is not making a lot of sense right now. Just kind of hang tight and you'll see where we're going. Number 5 says, what's the center of your approximation? So that doesn't have anything to do with this data in the chart here. That has to do with our graph. What are we trying to approximate? We're trying to approximate the cosine function right here at its y-intercept. So the center we would call x equals 0. Okay, that's the center of where we're kind of focusing right now. Okay, so quadratic approximation. So what we're going to do now is we're going to go back and we're going to use these equations and we're going to plug numbers into them. So f of 0, we're plugging 0 into that quadratic equation and we're plugging that in everywhere that we see an x. So that's going to give us I believe just a, because the other terms would go away. Over here, we're plugging 0 into our cosine function, which would give us 1. Let's go to the derivative. Okay, so the derivative, we plug 0 in for x, would give us just b. And then over here for the cosine function, the derivative would be negative sine of 0, which is 0. And then second derivative. If I plug 0 in, I'm going to get 2c because the equation was just 2c. And then over here, plug 0 in for x, and we would get negative 1. Okay, use the table above to find values for a, b, and c. Okay, so essentially what we're going to do is we're going to take our quadratic approximation and our actual approximation, and we're going to set them equal to one another. So if I set this a equal to 1, that means a has to be 1. Set b equal to 0, that means b would have to be 0. And set 2c equal to negative 1, solve it, and find that c would be negative 1/2. Okay, these three numbers are numbers that you're going to then go and plug back in to that quadratic approximation equation that we had back in the previous slide. We're going to plug these numbers in for a, b, and c. So that's going to give us 1 plus 0x minus 1/2 x squared. So that's going to create a polynomial. Let me write it as a polynomial. This is going to create a polynomial, a quadratic polynomial, that is going to approximate our function, which is kind of weird right now. You're thinking, like, how on earth could that approximate our function? But if you go back and sketch this parabola on the cosine wave, you will find that it would be an upside down parabola, and it would kind of look like this. And you'll notice that it does kind of hug the curve, okay? It's not exactly the same as cosine, of course, but it is basically taking a trig function and turning it into a quadratic or a polynomial, I guess, a Taylor polynomial. You're turning it into a polynomial that will kind of have the same x and y points at the center of focus. So if we're looking right here at the y-axis, these two functions do kind of have similar characteristics and actual similar y values right here in this middle space. Okay, so that's what the goal of Taylor polynomials is to find that approximation. Okay. It says, in the exploration, our polynomial approximation matched the value of cos x, its first and second derivative at the center x equals 0. Let's try to make that match more precise by using an even higher order approximation centered at x equals 0. So basically what we're saying here is we didn't do a whole lot of work to create this polynomial. It's only a second degree polynomial, but you can actually increase the degree of your polynomial, and the higher that you increase it, if you follow this pattern, the more similar it will become to your cosine wave. Okay, so bear with me. This is going to get a little bit messy, but we're going to go through, and because I want to show you how this works. This is going to help you with the actual lesson. Okay, so the quadratic approximation, we're going to go with a 6th degree polynomial. So we need the highest power to be 6. And remember, at the beginning, we don't know any of these coefficients. So we're just calling them A, B, C, and so forth. But we're not going to stop here. We're going to keep going because we want to have a 6th degree polynomial. Okay, the function we're approximating again is cos of x. So here's the idea. This big, long, messy thing is going to be similar to cosine, like almost exactly the same, actually. So we're going to go through and we're going to take derivatives over and over again. So the first derivative is just going to knock the a out. And it's also going to leave me with, remember, bring your power to the front, that stuff. So a little bit of a change here. All right, I think I got all that. First derivative of cosine is negative sine, so there we go. Second derivative is going to be 2c plus 6dx plus 12ex squared plus 20fx to the third plus 30 gx to the fourth. Second derivative for negative sine would be negative cosine. Okay, and we're just going to keep doing this. So if you want, you can fast forward to the end of this part where where we have all the derivatives written out, but you're basically just going to keep taking the derivative for these polynomials, okay? And be careful because the numbers are going to start to get quite large. And this part is pretty crucial to the end result, so you got to make sure that you don't mess it up. Okay, getting there. All right, two more. So we got 120f plus 720gx. I'm just going to keep going. And then the sixth derivative would be 720g. Over here, fifth derivative is negative sine. Sixth derivative would be negative cosine. Okay, so we have organized all of our information. The next thing that we do, like we did before, is we plugged 0 in for all of our x values. So we're using all these equations, and everywhere you see an x, you're plugging in 0. By the way, we're plugging in 0 because 0 is the center where we're focusing our attention right now, because we're trying to find an approximation for the middle of the cosine graph, and that's why we're plugging 0 in. I could do this same thing to find an approximation over here if I wanted to, but then I would have to plug pi in everywhere I see an x in order to get that value. So it's a little bit more work. That's why we're kind of just sticking with 0 right now. Okay, so plugging in 0 everywhere will give me, let's see, this will just give me A. I'm going to go through and list all these guys. B, 2C, 6D, 24E, 120F, 720G. Now, you might not notice it yet, but there's a pattern here with these coefficients. Maybe start to think about what that could be. The function we're approximating, so this is us working on that right-hand column and plugging 0 in everywhere we see x on that right side. So we get 1, 0, negative 1, 0, 1, 0, negative 1. And then solve for ABC. So remember, this is the step where we're going to take our value over here and set it equal to this number. So this is going to give us, and then solve to find the value of A, B, C, and so forth. So A would be 1, B would be 0, C is going to be negative 1/2. So those are not any different than what we had before. D would be 0. E is going to be 1 over 24. F would be 0. And then G would be negative 1 over 720. Okay, so now you're going to take that and you're going to put it all back together. And that means you're going to go back to this really goofy looking quadratic approximation. Not quadratic, this isn't quadratic anymore, but polynomial approximation. And you're going to plug in all the A, B, C values that you found. Okay, so that's going to look like, let's see, A. There is no B value, so we'll skip that part and go to C, which would make it negative 1/2 x squared. There's no D value, so the next one would be 1/24 x to the 4th minus 1/720 x to the 6th. Okay, now the little pattern I was trying to get you to identify is that these coefficients here, 1, 6, 24, 1, 27, 20, are actually factorials. 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, and so forth. So I'm going to rewrite my polynomial using factorials. Okay, so watch how this goes. This I could rewrite as x squared over 2 factorial. The next one I could write as x to the 4th over 4 factorial. And then x to the 6th over 6 factorial. Now, why would I want to do that? Well, I want to do that because I want to find a pattern. Because if I can find a pattern, I can kind of guess what's going to happen next. Like all this work I had to do, we had to do back here, we don't want to have to do that every time. You get what I'm saying? We want to find a shortcut. We want to find a pattern so that makes this process a little faster, okay? So I see a pattern now. I see that the top is the exponents are adding by 2 and that they're all even numbers. And I also see that the bottom are all factorials and the bottoms actually match the exponent. So it says cosine is equal to p sub 6 of x. That just means a 6th degree polynomial, which that is what we have because the highest power is 6. So it's saying, can you find an 8th degree polynomial? Well, yeah, all I'd have to do is keep the first few terms that I have, the 6th degree polynomial, and I would just want to add one more so that the next term is also listed. And now that I have created a pattern out of it, I can tell that the next term would have to be x to the 8th over 8 factorial. So that was so much less work than starting over from scratch. Now, why is this important? Well, this is important because this is just a series. Okay, this is a series. It's a pattern. I could write a summation for it. And we've been learning about how we can differentiate series, we can integrate series, we can approximate them a lot faster than we can complicated things. So that's why we work with series more often than the complicated things.